Yeah, we are now recording. So just waiting for the final few seconds before we could officially start. Okay, let's start. So this is week 3 of our course, uh, the Linux administration and shell scripts. So basically we are learning a lot of information about the operating systems, and our hands-on focuses are on Linux system mostly. So, I mean, like every week, we will organize our class today as well, a proportional mixture of some theoretical discussions and then some hands-on programming related to the operating systems. Before we start, let's talk about a few things regarding the assignments. So yeah, I mean, I see that most of you are submitting the assignments in time, which is very nice. Thanks to all of you for that. Some of the questions arises like when you do the quizzes, um, sometimes many of the answers look similar. So my suggestion on that particular issues is that, I mean, it is true that operating systems is a very technical as well as conceptual course, and it's not easy course, but I mean, in the class you are participating so much that things are becoming little easier for you, and more you like, not just the people who are present in the class, for everyone that listening to this lecture, either recorded or live. So more you participate in the class, especially hands-on sessions and also the question answer sessions, more your grade should improve. I mean, that's the thing. So every week we have a session dedicated for discussing the quiz answers. So basically all of your quizzes are answered during that particular session, particular hour. So try to utilize that one, because I mean, I mean, the quiz is yes, no type of thing, and then it is very easy to get distracted, and it is very easy to lose the points there. So that's why I'm saying that. And I mean, there are other options as well. Maybe sometimes you may think about, if you think that quiz is, I mean, if you're not sure about whatever quiz will whatever it will be asked in during the quiz, you can always, I mean, ask me for a review session with you one-on-one. We can do some review of the quizzes. We can do some review of the topics so that you feel more comfortable answering the quizzes. So that's another thing. Same thing goes for the assignments as well. I mean, the assignments are mostly, we do all the assignments in the class. There is no assignment here so far that is outside the scope of the class. We did it hands-on, and most of the students that participate in the class, they are doing it themselves as well by sharing their screen. So we do a lot of collaborations among ourselves. Uh, so if you follow the lectures, you should be able to solve your assignments pretty seamlessly. So that's another point. So today, actually, we are going to start some discussions on the memory management. Let me share my screen, and then we will start talking about the subject matter for today's class. So it's memory management that we are emphasizing today. Um, let's, I mean, there are a couple of things. I mean, the programs expand to fill the memory available to hold them. So that's the Parkinson's law about the memory, and also I mean, there are a couple of things. I mean, the second one is very astonishing that, I mean, in 1960s, by the time we sent people to moon, at that time, 100 IBM's, I mean, the best computer, the largest computer had some memory, and then nowadays every personal computer has 10,000 times more memory than that one. So we can imagine the growth of the field and how fast things are improving. It's not just, I mean, it's not just improvement in the application development software. It's also improvement in the technology. I mean, the chips, the I mean, different ways to get more memories. Right now, for example, the disks, like uh, 25 years ago, 30 years ago, disk, or even in the early 90s, the disk spaces used to very expensive. I mean, getting a 10 gigabyte disk was like getting everything in the world. But nowadays, I mean, the space is extremely cheap thanks to the development of the solid state technology, and we can get terabytes of disk seamlessly without any issue. So, anyways, I mean, let's start our discussions on the memory management. So, as I said, I mean, we will divide our class between uh, some. The first hour we will do some discussions. In the second hour, we will go to solve the hands-on assignments. Third hour, we will go back to discussions again. Fourth hour, we will do some hands-on, and that way we will evolve our knowledge. And then tomorrow, I mean, tomorrow's session at the end, last hour, we will be doing the quiz questions and answers in this class itself. So you remember what to write when you have the quizzes. I mean, we have been doing it for several weeks. So, I mean, we will continue that. So that's another thing. So let me jump into the memory discussions. So when we talk about the memory, I mean, you know what memory is, right? I mean, from human brain perspective, we remember something. When we work on something, we constantly remember, we constantly process information. I mean, everything is like memory. I mean, it's an important the resource that must be very carefully managed. Actually, the main memory in the computer is called RAM, or random access memory. So this is very important resource. I mean, the one you say, I mean, when you buy a computer, that's that's pretty much a parameter that we look at. Sometimes we say 2 gig memory, 4 gig, 8 gig, 16 gig, 32 gig. I mean, in the older times, it used to be 512 meg versus 1 gig, but now it is like 16 gig, 8 to 32 gig we get. So I mean, it depends on the scale you want. However, um, the memory is extremely important. So memory is RAM, and this is extremely important for your operating system. What programmer would like is I mean, every programmer like us, we like a private, infinitely large, infinitely fast memory, and that's also non-volatile, that is does not lose its content when the electric power is switched off. I mean, too much of expectations. While we are at it, why not make it inexpensive too? I mean, but right now we are not yet there. Even like we can get memory. I mean, we can the RAM, for example, you, it stays until your computer is powered on. Once you switch off your computer, you shut down your system, the RAM is gone. So it's not yet something that it remembers. But there are artificial ways to remember, like if you write it down somewhere. I mean, suppose the Amazon Web Service, when you not the web service, the Amazon e-commerce service that we use to buy the things, So, I mean, today I do something and then I just got bored with it, or maybe I have to do some other works. I leave my computer, maybe log out. Then tomorrow morning I go there and I still see that whatever my yesterday's activities were, they are still there. So they basically have a way to basically to remember the things. Basically they save it somewhere on their database or some storage, and then call it back when the session restarts. So I mean those are many options. So now if we cannot do, like, I mean, in a normal PC, computer, or your laptop, your device, if we cannot do that, like privately hold infinitely large fast memory which does not die with the resetting the power, recycling the power, or it is inexpensive. So what's the second choice? If we cannot do that, then what's the second choice? So um, over the years, actually, people discovered something called memory hierarchy, in which the computers have a few megabyte of very fast, expensive, volatile cache memory, a few gigabyte of medium speed, medium priced, volatile main memory, and a few terabytes of slow, cheap, non-volatile memory. So not to mention, I mean, you can also have the removable storage, the USB sticks. So it's the job of the operating system to abstract this hierarchy into into some model and then manage the abstraction. That's pretty much we are going to um, focus today. How the memory is managed. The part of the operating system that manages the memory hierarchy is called the memory manager. You know what is a memory manager in an operating system? The part of the system that manages at least a part of the memory hierarchy. So when you have the memory, you have the main memory, you have, I mean, hierarchical memory is like memory has a hierarchy. In the top, it's very expensive. It's a like a volatile memory, and then you have uh, as we go down, we have the expense becomes less, the connectivity becomes slower, but then the memory becomes more stable. And at the end, we have the disk. That is the final ultimate memory. This is slow, and this is, I mean, this is permanent memory. So you can save your data into there, but that's not very fast or very, sometimes it's not very useful. I mean, accessing disk is very costly, uh, about it. So this chapter, this today actually, we are going to understand some memory management models. You know, so as it says, the in the early computers, I mean early mainframe computers, so they did not have this memory hierarchy or memory abstraction model. So what happened there is that the programs that you were running, if you use that early days computer, then you would directly access the physical memory. There is no virtual memory. There is nothing like for a person, nothing on my brain. I'm just writing down everything, things like that. So computers were like that before. And then, I mean, typical instructions were like, I mean, you see here, move register 1000. That means something, some register, some hardware, whatever data is going there, that is moved into, literally moves to the 1000th block of the physical memory location. So we would do everything by hand. I mean, you can see that physically the memories are stored now. um, so that was very slow, that was inefficient, because you could not run a lot of processes with that, because at a time only one process could run. So that uses that physical disk space where you call memory, and then the next process comes, and then it uses another part of the memory. That way it went on, and it was not very efficient. But as a programmer, the way we view the memory is simply a range of addresses. representing the physical memory cells. Like we say 1000, 2000, those blocks, those are the addresses. So, I mean, in the old time, I mean, old computers, the lack of memory abstraction prevented multitasking. Multi-programming model was not possible with those abstract, I mean, non-abstracted memory. Like the physical, everything is physical. So writing a new value to a memory location could override data stored by another program, causing a lot of failures. I mean, yeah, so I mean, in the I mean that happened. That used to happen earlier times. Even I mean, like in the early 90s, we could see that if we do a lot of things with the computer, it used to get confused, you know. And then simple output programs, uh, we had to sometimes that did not respond properly because somebody else was using the same block and they overwritten, they start overwriting the things that other people are doing. So a lot of collisions used to take place, but that was the time when we did not have any proper memory hierarchy in place, which we are discussing today. I mean, during the presentation, you are always welcome to ask, speak up. That is good actually. So we can have a good discussion, good collaboration in the class. So I encourage you to ask questions, and it doesn't have to be very sensible question at all. Any question is good question. So you can have different memory organization options. I mean, that's the next topic that we are jumping into. So we are making some progress with the memory management model. So if we do not have any memory abstraction, there were variations in the memory organization, you know. So the variations are pretty simple. So we can see it in the picture itself. I mean, three different ways of organizing memory with an operating system and only one user process, you know. So what is this? What does this is it? What does it say? So the operating system may be at the very bottom, you know, everywhere. I mean, here A in the figure A, operating system at the bottom of the memory in RAM, random access memory, or it may be in the read-only memory at the top of the memory. So it can be uh, there are variations, you know. Now, the device drivers may be at the top of the memory in a ROM. I mean, like there are three different options of managing the memories. So, first option, operating system is at the bottom, user programs on the top of it. The second option, the I mean, it is like operating system in the like read-only memory. Operating system is in the read-only memory and the user programs in the bottom. The third option was the device drivers in the read-only memory. User programs are coming next, and then operating system is residing in the RAM. So exactly like A, but the user program and device drivers, they are a little bit. I mean, they have some mixes out there. So the first model, the A, actually was formerly that was used on mainframe computers and mini computers, but it was not used anymore because it's very elementary. The second model was used on some handheld computers and embedded systems. The third model was used by early personal computers like MS-DOS, the Windows system, very old system, where the I mean portion of the system is in the ROM called the BIOS, basic input output system. So models A and C have the disadvantage. What is that? The disadvantage is that a bug in the user program, you know, the bug in the user program could wipe out the operating system as a whole, possibly a disastrous result. You know, some user goes to the system and they, I mean, typically, I mean, people didn't know how to manage the memory. The user goes to the system and it's not very hierarchical system, and it's very elementary system. They want to basically they create programs that would stop the memory management processes, or they make some mistake somewhere and that is injected way into the operating system itself. Sometimes what happened, I mean, like, people wanted to clean up the computer, and I mean that typically happened. I mean, it's true, it happened in front of me. Like, people wanted to clean up the computer and they literally removed the, the the system file because it was accessible, and it's not in the memory. It's accessible, and once you delete it physically, there is no way computer could retrieve. So people cleaned up the system files, few megabytes. That time it was very costly space, and then next day the computer could not boot up, so they had to restore the system. I mean, those early Unix times, it was the situation because there was no hierarchy. That's because there was no hierarchy in the system. The systems, I mean, right now it is impossible because I mean, you would not. I mean, the memory hierarchy is done in a such a way, in a partitioned way, that you cannot even go into your I mean, kernel space. You have the kernel right now, where your operating system lies. I mean, that stays there, and as a user, you don't have any access to the kernel. In fact, in order to do any systems call, you have to request to the kernel, and then the kernel will vet your request. I mean, it will see whether it's a valid request, and then it will process. So there is a process hierarchy when you call something in the memory. So you cannot directly access any memory right now. You have to do the calls. So that hierarchy was missing in the early days computer, and there were a lot of disasters results as such due to that fact. Now, when the system is organized in this manner, actually, only one process at a time can be running. I mean, this manner means this whatever we show here in this figure, if we have something in this way, this architecture supports a single user. I mean, single user, also a single process type of machine. So the multitasking or multi-programming model was out of scope within that architecture. So when user types a command, the operating system copies the requested program from the non-volatile storage to memory, and then it executes it. When the process finishes, the operating system displays a prompt character and waits for a user new command. And when the operating system receives the command, it loads a new program into memory, overwriting the first one. So it was simple, but it's not very efficient one. So one way to get some parallel operation in a system, like you have 5, 10 tasks running at the same time with no memory abstraction, is to program with multiple threads. You know, we just discussed threads last day. So since all threads in a process are supposed to see the same memory image, the fact that they are forced to is not a problem. While this idea works, it is very limited. It has a very limited use, since what people often want was unrelated programs to be running at the same time. Sometimes the threads abstraction does not something that the threads does not provide. You know, the as per our hierarchical discussion last week, we have the program. Program is the algorithm. Then I mean, it's a written text. Basically, it's a text file. It's written in some programming language. Then once you run the program, then it becomes a process. Under each process, you have the threads. So when you have a program or process, it's impossible. I mean, the program and process can do one simple task. Let us see. Let us say. So this task has multiple threads. So independent, unrelated task management is not that possible with the threads which belong to a single task or single process. So the thread model of accomplishing the tasks without any memory abstraction is not very effective process. Any system that is so primitive as to provide so many abstraction is unlikely to provide a threads abstraction. So I mean that's the problem of running multiple programs without a memory abstraction. However, even with I mean, let's say there is no memory abstraction, it is possible to run multiple programs at the same time. How you do that? One is the thread model, which is not multiple process, but the operating system, what it has to do uh, to is save the entire content of the memory to a file. The memories are saved in a file on non-volatile storage, then bring in and run the next program. As long as there is only one program at a time in memory, there are no conflicts. But then if you, I mean, so basically what happens, you have a file, then you write something here, then comes the second process. Once the second process triggers, the copy of this content from the first process is moved to somewhere else. Then the second process comes, it writes something, and that way basically it's swapping of the process content across different sections of the disk can take place, and that way you can run multiple program without any abstraction of the memory. So, I mean, with the addition of some special hardware, it is possible to run multiple programs concurrently, even without swapping. I mean, simple way is, suppose you have the disk, you have 5 disks, and then you run the processes on 5 different disks parallelly. So you can each of the disks can do like non-hierarchical physical memory, can use the physical memory, no virtual memory, just writing something, reading from there, things like that. The early models of IBM, I mean, devices solved the problems as follows. I mean, it was like that. The memory was divided into different blocks. I mean, 2 kilobyte blocks, and each was assigned a 4 byte protection key held in the special registers inside the CPU. A machine with 1 megabyte memory needed only 512 of these 4-bit registers for a total of 256 bytes of key storage. So basically, um, without any, I mean, lot of terminology, lot of numbers, without memorizing those things, I mean, you divide the memory into the blocks, and then you use those blocks, you know, and the blocks are protected by some mechanism. So that was the way the early days computers, IBM 360, that solved the problem of multitasking by a computer. But the solution has some drawback, Um, so it has some um, we have already discussed all these things, so I'm just um, fast forwarding. So the solution, the one we talked just now, it has some drawback. I mean, this drawback is let us discuss this one. Like in this figure, we have we can show two programs in the A and B, in A and B, JMP24, JMP28. I mean, there are two programs running. So the former, I mean, the this one, the first one is is this indicates that it has different memory key than the later. I mean, they use different color code to exhibit that, because otherwise everything is same. So the first program starts out by jumping to address 24. You can see here clearly jumping to address 24, which contain a move instruction. Then the second program starts out by jumping to address 28, which has which contains a um, some some instruction, CMP instruction. The instructions that are not relevant to this discussion are we don't show those. But when two programs are loaded consecutively in memory, starting at address 0, we have the situation in in the figure C on the right hand side. Basically what happens here, the program, after the programs are loaded, they can run, but since they have different memory keys, neither one can damage the other. But the problem is of different nature. When the first program starts, it executes the JMP24 instruction, which jumps to the instruction as expected. The program functions normally. However, after the first program has run long enough, the operating system may decide to run the second program, which has been loaded above the first one at some arbitrary address 16384, let us say. See this picture, the second figure. So you can see the different memory address locations or blocks. The first instruction executed is here in the second case, JMP28, which jumps to the add instruction in the first program instead of CMP instruction as it's supposed to jump to. So the program will most likely crash as well. Within a short duration of time. So what is the problem here? The problem here is that two programs both reference absolute physical memory. That is not what we want at all. Two programs are trying to acquire the same space in the physical memory. We don't want that. So this can be, it is later solved in a different way, but that that part we will take later. But in the current computers, in the modern context, so the computer systems like the mainframes, mini computers, desktops, notebooks, and smartphones, the direct addressing of the physical memory is not required at all. So the memory abstraction is still lacking in embedded and smart card systems, different flavors of operating systems. So the devices like radios, washing machine, and microwave ovens often rely on ROM software without absolute memory addresses. This works because all programs are predetermined and users cannot run their own software on these devices. That's a severe drawback. For example, if you have your smart TV, it has an operating system on it. So that's an embedded system. That's an example of your embedded system. But then you cannot load your own program on there on the smart TV. So you cannot write a program and just load there. You have to, of course, you can load program through the marketplace. That's a different concept, but you cannot run your own software there. So when you run something from the marketplace, there is some memory management. That model is also included, some register takes place. So that's a different way managing the applications, but you cannot run your application on the smart TV on demand. So that's the point. So in the modern concept, so we understand that in the contemporary computers, basically direct addressing the physical memory is not used at all. So the memory abstraction is still not good in the embedded and the smart card systems. Like the devices like radios, washing machine, microwave ovens often rely on ROM software. Um, with the absolute memory address. This works because all programs are predetermined. That's what I said. Like when you download something on your smart TV, that is predetermined, and it also downloads the memory management, alters the memory management schemes. It knows about that. There is a program. If I download, I have to change, alter some things here. So these are predetermined. You cannot put your program there and on an ad hoc basis, you cannot start, get it running, basically. So history often repeats itself in the computer world. The computer science we have seen, like Intel 86 processors introduced advanced memory management and isolation features much later than IBM 360 protection keys. Intel incorporated the seemingly old-fashioned protection keys into its CPU in 2017, and I mean that's long enough after IBM's introduction of this enhanced, I mean like the memory management. The simpler embedded systems may lack elaborate operating system, and the operating system functionality is provided as a library linked with application program. The ECOS operating system serves as a common example of an operating system as a library. So that's a name basically. So it's a pretty new concept. Operating system is loaded as a library, and then once the library is loaded, you got your operating system loaded. I mean, it's just like virtual box, similar to, not exactly same, but you did the virtual box. So basically you installed an operating system there. Virtual box provides you with a very basic operating system. Everything is predetermined. You cannot simply, you can add programs, but you cannot just start using VirtualBox out of nothing. You have to have some predetermined program installed there. Linux, you have to install Windows. VirtualBox itself will not provide you any system level functionality. It only can hold certain operating systems. So it's an embedded system, but it has it's not very advanced thing. I mean, as far as only VirtualBox goes, it is a container kind of thing. So embedded container where you can host different operating system. That's it. That's your VirtualBox. So next topic is the memory abstraction problem, the address spaces. So basically what you do here, you expose your physical memory to processes that has significant, I mean, basically exposing your physical memory to process is not good. That's what we learned, right? So if the programs can access every byte of memory, then uh, they can unintentionally or voluntarily, deliberately disrupt the operating system. That can cause a system issue. you know Running multiple programs concurrently becomes challenging without any memory abstraction, any hierarchical structure of the memory. The personal computers commonly run several programs simultaneously, with one having the current focus while others remain active in the background. Sometimes we run program, our PCs run program in that way. To address these challenges, a new abstraction called address space was introduced. you know so address spaces aim to enable multiple applications to coexistence to co- to exist at the same time in memory without any interference. So it solves two problems: protection and relocation. So the IBM 360, for example, it used a primitive protection solution that we discussed few slides ago by leveling the memory chunk with protection keys, comparing them to the executing process keys. So, I mean, that has a protection basically, so that memory used by program one cannot be claimed by the program two. That's the protection it has. However, this approach does not address the relocation problem, which requires a slow and complex program relocation during the loading. So we will talk about it later, the relocation issue. So what we understand is that, uh, I mean, the, if you want to expose your physical memory, the physical disk space into to the processes, and that if that is the way you manage the memory, then that is not a good way. You know, it has a lot of drawbacks. We saw it before. Now, if user programs can access every byte of memory, they can unintentionally or deliberately can cause harm to the system itself. So the address spaces are something like the blocks. Address spaces are like the blocks. You divide the address into multiple blocks and assign address space to them, each of them. That can be a good model to start the memory abstraction, and IBM 360 used such a model. So it has some limitations as well. So a more so what we do, we are abstracting the address space here, which creates an abstract memory for the program to use. Just as processes create an abstract CPU to run programs, address spaces provide a set of address for processes to across the memory. So think about uh, the whole memory. It is divided into different blocks. Each block is called address space. And you can then, if you can create some partition, as I said before, then you can run independent programs within the address spaces. If there are 10 address spaces in your computer, then in principle, using some some modernization, some partitioning, you should be able to run 10. If there are 10 address spaces, you can run 10 processes there. So each process can have its own address space independent of other process, except in specific cases where address space sharing is needed. Address spaces are not limited to numeric representations. I just told you the block address, but it may be anything. It can include the telephone numbers, input output ports on x86 systems, and there are IPv4 addresses as well. The address spaces can also be not numeric, such as set of .com internet domains. So it does not have to be any numeric block. It can be anything, something, some area where where which is used for doing certain tasks. So you are not overlapping the address spaces to each other. That's why the set of tasks could execute in each of them without interfering or without talking to other tasks. So um, the simple approach, the easiest approach to address implementation address space implementation. How do you implement that address space is basically you can use the base and limit registers. So this method allows mapping each process's address space to a different part of physical memory. Programs are loaded into consecutive memory locations without relocation during the loading. When a process runs, the base register is loaded with the physical address where the program starts, and the limit register is loaded with the program's length. Whenever a process refers memory, the CPU hardware automatically adds the base value to the process generated address before sending it to the memory bus. So basically, when you use the address space, basically, so you are dividing the memory into different address space, partitioned address spaces. So you can use the registers to handle that partitioning and that messaging that a process is created. So that's a message, kind of the message driven framework. Um, so basically the hardware checks if the address exceeds the value value in the limits register. So hardware can check those things. The hardware simultaneously, at the same time, if the address is equal to greater than the limit, a defect is generated, terminating the access. This mechanism allows correct memory access even when programs reference addresses related to their individual address spaces. So basically, we are trying to understand the memory management. Let's little bit recapitulate whatever we did so far. We were trying to understand memory management, and there we saw that the early computers were doing some using. There was a tendency to use the physical memory that has some limitations as we talked about. But then there are multiple solutions. The main limitation was multi-programming was impossible. But now with advents of different directions like creating the blocks or creating the address spaces for different processes, that can help us in running the program, and also at the same time basically abstract out the memory blocks and use them properly. In the I, I mean, in the very first class I said the goal of the operating system is to optimize the use of the system resources. Memory is a system resource. So we are basically, by implementing some address, I mean, like the memory memory management process, we are making the processes, our devices, more efficient. So let's do a break, and let's come back at 7 p.m. and we will develop the concepts. But at 7 p.m. we will be doing some hands-on exercises. So we will be doing together the assignment one. Be ready. One of you are invited to share your screen, and while you solve the problem, we will all watch and we will be talking through that. I will be uh, guide you step by step in the solving the assignment problems. So next hour is our hands-on hour, and we will spend good time with our tools. I mean, be ready with the Linux Mint. Be ready with your virtual box, and then start up the Linux Mint, and we will do some exercises there. So let's come back around let's say 7 p.m. Let's come back around 7 p.m. and we will go from there. On your computer. So let's open a terminal and then we will start. Yeah. Okay, that's good. The terminal is up and running. So so basically we are using a terminal, you know, it is a command line interface for any machine. So that's what we are using. Now, so this user, the one you have, I think that user has administrative privilege. So can you do sudo su? Can you type sudo sudo then space su, enter, and then you can do the password for yourself. Enter. So yeah, so you are in the you have landed into the root user. So basically, while you are Shiloh, I mean your own user ID, but you are acting now as a root user. So one thing that is clearly visible, everyone look at the terminal, you can see that when Shiloh was as a user, common user, his prompt was dollar, but as soon as he logs into the system as a super user or root user, his prompt is converted into hash or pound, whatever we say. So that's the difference. I mean, that's the difference between a root user versus the normal user. When you look at the prompt, those will be different. So that's an important thing to remember. You know, when we do the Linux course, I mean, when we learn the Linux hands-on, there are a lot of certifications in the market. Uh, Maybe at some point you will consider those, but in general, without even doing the certifications, as a user of Linux system, we need to know these prompts. I mean, these simple things. Anyways, so now we can use the user add command. So we did little bit in the first class. but let's do it again. So do user add, type user add, then -m, uh, then -s, the bean. So do the /bin /bash, and then you write your username. What your name actually? That's your username. Yeah, it's starts with small letter. Yeah, enter. So you this user already exists. So give it a different name. Just give it something different. Some another user. You can add another user. You can do you can click on your page up arrow. You will get back that function. So if you do the page up arrow, I mean there is an up arrow, down arrow. Yeah, that's it. So give a different name to the user. So you are creating a different user, Steve. Yeah. So your Steve is created. Uh, so what it says basically, I mean the, the basic shell. You know the Linux works as a shell program. Whenever a user log into the system, then you create a shell. I mean it does all the commands as a part of the shell. The fact that you can do the up arrow and down arrow and can get back whatever commands you have used, that is the feature of the bash shell. You can have a shell that does not have that property at all. So so different shell behaves differently. So in the Unix, in the Windows system, the system that we normally use, I'm using Windows right now, for example. It has only, I mean, if you go to the command line, you will find just only one prompt. We will be discussing the Windows PowerShell in the next course. Actually, there is a separate course for that. But just making a comparison, when you are within Windows, you have only one system where you can do any programming. I mean, any command line commands, whatever it is. But with Linux, actually, you can have options with different shells. A shell means it's a controller on how you are executing your programs, you know. So basically you can have bash shell. This is very popular. You can have Z shell, ZSH. You can have simple SH, simple shell. You can have a lot of different shells are there, you know. Um, so we are now focusing on the bash shell. Now let's set the password for a new user with the password command. So let's do PASSWD, and then you write your username space Steve. I mean the new user that you have created. So enter. So you can give a password to Steve. Give a simple password that you can remember.
Oh, okay.
Yeah, do that. So now you have created that user, and can you go and do ls /home to verify if your slash, not the dash, /home. Yeah, home, and see if we have created the Steve user. See, you have Bob, you have Shiloh, you have Steve. So Steve is the newly created user. So we have learned how to create the user account. So hopefully next time you will do a different user as well. So what you can do, I mean, you can take a screenshot of this activity and put it inside your Word file. That is part A of your exercise for this class, for this particular assignment. Now uh, we can move on, and now we can try to, now we create the user account. Now we can modify the user accounts. So for modifying the user account, remember this user add, you could execute this command as a super user. So in order to do all these things, adding a user, modifying a user, uh, someone has to have the super user privilege. A super user can only do that. Someone with the super user privilege can do that. Myself, for example, if I'm a user of my company's computer system, I cannot use that. I cannot do any such user creation unless I'm the system admin or super user. So so let's do some modification of the user. So as the assignment says, let's do user mod. Let's write user mod, okay, space -l. So give a new username. I mean, whatever username, I mean, instead of Steve, you can do some username, whatever it is. Don't write new username. It doesn't look good. I mean, you can do another name. Let's say instead of Steve, yeah, Tom, and then you can write Steve. So you are basically renaming your user. So enter. So now if you do ls/home, you should be able to see Tom. I believe that's what you should be seeing. So no, it is still there, but what is happening here? So basically, you are changing the username. So what is happening? The old is Steve, new is Tom, but you should be able to see the Tom somewhere. So
Did I
so
type something wrong?
No, I don't think you did anything wrong. That's what user mod is for. But the username should have changed. I mean, user mod minus. Yeah, I mean you did right way. That's what we are supposed to do. Yeah. So Steve doesn't exist. So even if maybe the directory is the same, but maybe the directory remains the same, but your username is different. That's what you see here. So if you want to log in into the system as as Steve, you should not be able to do that. So can you do SU Steve, super Steve? I mean like uh, SU Steve. Is it possible? So it doesn't exist. Can you do SU Tom? SU, then Tom. Yep, Tom, Tom. Here you go. So you can be Tom. You cannot be Steve anymore. But the folder name remains the same, but the username changes. So that's something we can do to modify a user. Now you can, of course, we have altered the password. So you can do exit so that you exit from Tom space exit. No, exit exit. Yeah, enter. Yeah, now you are back as Shiloh, but as a root basically. So you can alter the password for Tom. We are not going into that exercise. We have already done it. Now let's do something. We want to view the details of the user account. So for that, the command is the ID command. So do ID and then space Tom. Enter. So you see here, the user ID is there, 1002. Tom is the username. GID is called the group ID. And you know the group ID is Steve because the Steve user has been renamed to the Tom user, but the group space is not changed. And also the groups, it belongs to the group, only one group, that is 1002, which is Steve. So by default, so what we learn here, two things. Number one, when we press ID, when we do ID and then followed by the username, then you should be able to see uh, the the information about the user. But what information you will get? Three pieces. Number one is the user ID, which is a number, And also in the parentheses, it mentions about the name of the user name. Then it emphasizes the group ID, which is another number, and then you have the username, but that name is the old username because we did not change. I mean, having a user mod run, I mean, renaming a user does not change everything that it belongs to. It is still under the group ID, a group name of Steve, and it is under, I mean, the groups means you can have Tom to 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 be under 5 groups. You would basically see 5 different IDs and the group names there. But here by default, when you create a user, it belongs to the group name, which is same as the username. So those are the things that we could see here. So uh, basically, that is the way we can identify, we can see the information about the user. Now let's go to part C of this assignment. Now let's manipulate the groups. So you can do a command called group add, like user add. You can do group add, and then you can do some group name. Make up some group name, just arbitrary group name, whatever it is. Test, maybe. Yeah, okay, that's fine. Test, okay. So enter. So you have created a group. Now, what you can do is that so basically you have created a group. Now, what you can do, you can do an user mod command. You can put Tom, add Tom to that group as well. So how do you do that? You have to do user mod. Yeah, -a -g. -g corresponds to group. So then you do the group name, whatever group name, test, uh, test, and then Tom, space Tom. Okay, enter. And now if you do ID Tom, you should be able to see the group that it is under. So you see here, you have its primary group ID is still 1002 or Steve, but it is now under 2 groups, 1002 Steve and 1003 test, the one you just created. Now, why would someone put a user in different groups? Any insight? I mean, brainstorm something, suggest something.
Different security access?
Of course, yeah, that's a good option. That's a good thing, security access. So basically, you design some resources and groups act as security to those resources. And as you add a user to that particular group, that user can have access to those resources, maybe a file. So in the Windows system, uh, for example, I'm giving you an example. For example, you are working in a company, right? So you are on a Windows server that everybody uses. Now you go to the Windows server, you go to a iDrive. Let us say, I'm just arbitrarily, it has nothing to do with any specific example. Brandon, do you have any question? I just see you have raised your hand.
Yeah, when I do group add,
Mhm.
it says permission denied.
Because you are not, did you do SU whatever the username, like the first command in this line, that is sudo su duo su. Your prompt, if it does not look as hash, your prompt like Shiloh, home Shiloh, and hash sign represents you are a super user. If it is not, then you cannot add a group. Can you try it and let me know if it works for you or if it doesn't work for you?
Yeah, I did SU and then my username,
No,
then ask for
not su your username. You should do sudo sudo space su. So basically, you are pretending as a super user. Sudo is like pseudo, the pretend. You pretend yourself as a super user. So sudo space su. Can you type
okay.
that?
Yeah, I got it worked now.
Okay, yeah,
Thank
that's a
thank
good
you.
deal. Okay, no problem. So that's the usage of our collaborative session. We can solve our problems here. So that's good. Okay, now so basically you can see that a user can belong to multiple groups so that they can share the resources assigned to specific groups. So you can create a file under, and then we can show later, you can create a file, and that file, maybe we can turn on access to that file. Let us say read access, write access to that group. So suppose you are on your company's computer, you work for a company, let us say, then I go to, let us say I go to iDrive, and I see there are a lot of folders there like human resource, HR. Then I see a folder named confidential, let us say. So does that mean that I can see the confidential information? Answer is no. I mean, if you click there, you will see that you don't have permission to view that. For example, you don't have permission to go to any other Teams folder. So in the Windows system, we will discuss that in our upcoming course, how we do that in the Windows system so that we can correlate ourselves more to whatever we are doing, because most of the computers today are Windows computer. But in the Linux, right now we are discussing about the Linux. So basically, if you don't add a user to a group, which is done here, if you don't do that, then that user cannot have access to the resources that is within that group. So that is a security provision created by the operating system, and that security provision is very configurable, and it is doable by simple users. I mean, on the command lines. So that is something we do, the group. So then let's move on, and let's try something else with the group. Now we can do the change the primary group of the user. So when you do ID Tom, you see the GID is 1002. That is the primary group of Tom. Now we can do like this. I mean, let's do user mod again. User mod minus small lowercase g, yes, and then you do the group name, whatever it is, test. Let us make it test, and then Tom, enter, and then ID Tom. What I should expect is that my primary group as a Tom user, his primary group has changed to 1003 instead of 1002. So that is another thing. I mean, like maybe the primary group test has some set of files. Let us say, I mean, what is the purpose of that? Let us say in an organization, you have different files, different information. Now, the whatever in the test folder, test group, I mean, whatever assigned within the test group has some, let us say everyone belonging to that group as a primary user, I mean, primary group user has the right access to that file. If we can do that, then we want Tom. Tom got promoted, and he has now, I mean, access to the confidential information. He becomes executive, and he has access to the confidential information of the company. So that is the usage, basically. That is the typical use case. The system administrator will simply modify the Tom's user, I mean, Tom's user ID, so that that can belong to now test as its primary group. So that person, that user can access the specific, I mean, more hierarchically, more confidential information. I'm giving the example again. So that is the use case for modifying the user and assigning the user to a definite group, I mean definite primary group. Now, if you want to just view the groups that a user is attached with, so you don't need to do ID always. So you can do groups. Can you type groups? Groups, GROUPS, yep. And then username, Tom. Let's see, not the Tom. I mean, you can see Tom's primary group is test, but you can do the groups test. Then you can see who are the users within that group. So no such user. So basically, oh, sorry, I messed up. So basically, test is not a user. So this command works in the way that groups, and then you give the username that will give you what are the groups a particular user is within. So that's a command. So I mean, let's try something. I mean, I'm not sure about that, but let's try this. Let's create another group. Group add, right? Group add, and then yeah, group add, and then create another group. Not test. I mean something else. Yep. Enter, and then let's do user mod minus a capital G uh, minus a capital G, then test2 Tom space Tom. Now let's do groups Tom. I mean space, enter, and now do groups Tom. So you can see now that Tom is, I mean, Tom is added to group test and test2. So that's how you can see, I mean, by the group, by the username, a user, what are the groups it is attached with. So this is the way you can do it. These are all the system administrator level commands for the Linux system. So these commands are essential for administrating the Linux system.
Can I ask
Now,
a question?
yeah,
I do
go
too
ahead.
when you're done.
Okay. Yeah.
So if you had like you were saying that Tom could be he gets a higher security or something for like the confidential stuff and tests. So if he's in 5 groups, does each password for every group he's in have to be different, or are they all like? Would you give him like different passwords for each one?
No, I mean, that level of granularity, I don't think that is accommodative in the Linux. So what you do here, a user will have unique username and password. The credential should be unique to the system. And groups are the this is a very good question actually. The groups are the subdomains of the system. Within the same machine, same user hierarchy or groups hierarchy, groups are different partitions within the system. So for accessing a particular group, you don't need any password. I mean, so long as someone with a role of super user adds you to different groups, all the activities in those groups should be visible to you. So you
Oh,
don't need any password. So that's the answer.
so as long as he has his own password to get onto his computer,
Yes,
then he
yes.
can get into any of those groups.
Right. I mean, it is comparable to the roles in the system. Like for example, you have, let us say you have a information system, and you can have different roles and permissions on the system. Suppose you can delete certain resources. That's a role, and you can view something, that's another role. So if you are given if you are added those roles, you should be able to view a file, you should be able to delete a file. It is something like that, but the groups are different. Groups are essentially the partitions, I mean partitions or collections within the system. So the under this collection, you can add the objects. So objects are, user is an object, the file is an object. So anything that directory is an object. So any object within the system can be can be assigned to a group. So that's how it works. Yeah, that's a very good question. So what was the another question, Jennifer?
Yes, so on Shiloh's screen, the lime green, if you go down maybe like 6 or 7 there, where it's UID 102 Tom, GID 102 Steve, and then groups 1002 Steve. And then he's in the test as well. So when you go down a couple more and he does groups, Tom, no, I'm sorry. When he did the user mod below that and the -G test and made test his primary group, why does it take away the groups equals 1002?
Yeah, because basically what happened here, this is also a very nice
Did I miss
question.
that one? I don't know if you said it and I didn't get it. Okay.
I did not explain it. Yeah, that's a very good observation. So what happens here that by doing by assigning Tom a primary group to a primary group different from its default one, you are basically evicted this user from that group because it is unless you add them. So what happens here, there is a primary group for a user, so that is there with the user by default. Then you add a secondary group, another group, not secondary, another group, so they will add up to a list. But now what happens, the user Tom was already within the primary group of 1002, maybe Steve it was named. So it was under the group named Steve. But what you did here in that line, actually user mod -G test Tom, you altered that user's primary group. So
okay, so maybe when a user is very first created, they go into that default and they're just a user, they don't have any access yet, and once you assign them, then okay.
So that's pretty much the system did to that user. That's a very good observation and good question.
Thank you.
Yep. Okay. So now what we can do, we can delete a user group. Basically, can you do group del and then test? Can you do group del test? Let's see what happens to user Tom now. Group del. No, this is a single command. Group del and then test. So if you enter, you cannot. So that's the security. That's the checks and balances within the system. You cannot remove the primary group of the user. So what you can do here, you can, let's try group del test2. So you see that I mean you cannot drop just a root user from the system. Test2, yeah, enter. So you can do that. And now if you do ID Tom, let's see what happens. So it is under just only the test group. So that test2 is deleted. So basically the rule is, if the when you issue the command group delete group del, then it does some checks and balances. It does some checks. If that group is a primary group for a user, then you cannot delete that, because then the user will become orphan. Basically it won't have any group. A user by default in the Unix system, in the Linux system, must be within a group. That's the criteria. So that's what is reflected here. So you can see here the operating system has created certain amount of security around it, so that any evasive action, doing any evasive action, is even impossible by the super user as well. I mean, they cannot simply delete a primary group of an user, thereby making that user invalid user. So that's the checks inbuilt in the system.
Would that be
So-
like a directory if you had files in order to delete the test
Uh,
group, you would have to delete Tom from the group first and then delete the test group?
Actually, the directory is organized in a different way than the groups. I mean, the security around different objects are different in the Linux system. So groups are kind of like logical partition. You know, it does not have any physical like you cannot go to a group by you cannot go and visit a group basically. So but you can browse, you can change your directory to a certain directory if you are granted access to it. So that's the difference between a group and directory. But in a directory, for example, if you have a file in a directory, I mean, you can always delete the directory, including the files. But if you use the command rmdir and then you do the directory name, it cannot delete the directory if the directory contains some files. I mean, this is something similar to the groups, this behavior, not the inherent function, but the behavior from the behavior perspective, if a directory is empty, then you can delete it using rmdir command. If the directory is not empty, you cannot delete it using rmdir command. It will complain. But you can do some other command, rm-r, recursive delete, recursive remove, in order to get rid of the entire content, wipe out the entire directory with all the sub directories or all the files within that. So does that make sense?
Yeah, I mean, I was asking because what if Tom gets fired or something, or Tom doesn't need to be in this group anymore? He gets to go to a higher group and they don't need him in this group no more. I mean, why would
So
they?
then you do the you should drop Tom from that group.
Oh,
There
okay.
are other commands for that. We will discuss that. But I
Can
mean,
you add them back to the default group ever, or once they leave the default
yeah,
group,
of
is it
course.
gone? Yeah.
Okay.
I
Okay.
don't think so. I don't think so. You can do that. I believe. So you can do user mod -g and then test2 Tom, or -g Steve Tom. You can try it. Let's try that. User mod -small g, and then you can do Steve and Tom. Enter. So now ID Tom. So you can do that. So basically, yeah, you can reassign Tom to that group. So that's basically some way to, I mean, adding and removing the user from certain groups. But there should be a command by which you can remove a user from the test group as well. So we will find that out.
Okay.
Let's move forward with the exercise, but that's a very good question. We will mark it. I mean, I will mark it and I will find it out for you. Now let's do some permission and ownership that goes back to some of the questions we were talking about. If Tom gets fired, then he gets promoted, or his role changes, he changes the department, then what happens to his previous I mean privileges? So that's what we deal with the permissions. Now we can do the chmod command to set permissions to the files and subdirectories. So basically chmod is the change, I mean chmod. So basically what it does, it it changes the permission for different files. So let's say let's create a file. I mean, don't use the chmod command as yet. Let's do source. I'm sorry, touch touch xyz. So we are creating a file xyz. Enter, and then ls -l minus L XYZ. Okay, XYZ
Oh,
is there.
sorry.
So yeah, that's fine. So when you look at the line for XYZ, what do you see? Like you see in the first column, I mean, there are set of dashes and letters.
Read right.
So the first word, so you see we are focusing on XYZ. I mean, let us do LS minus L XYZ. Then we will be more focused. We will know exactly what we are talking about. Enter. Okay, now we are focused on XYZ. So you see there are, I mean, it starts with the dash. The representation starts with the dash. Then you have R, then you have W, then you have dash, then you have another R, then you have dash, then you have dash, then you have R dash dash. What do they mean? So the first dash represents that it's a file. If it were a directory like the videos, see above the videos, the blue videos, it is D, the first word. It means it's a directory. If it is dash, then it's a normal file. Now RW, so it means you have the user, the current user has read, current user is root basically. They have read access and write access, and there is a dash. So the dash represents the execution access. So this user, this file is not executable by the root user. Now the next set of characters are R dash dash. Let's consider, let's do the first character, that is dash first. I mean, I'm restarting from the left. Let's start with the dash first. That is file or directory. Then we have three characters. Let's consider after that, let's consider three letters at a time. So RW dash means this user, root user, has read access, write access to that file, but it does not have execution privilege on that file. I will show you how to add that. Then next three letters are R dash dash. What does it mean? It means the group. I mean the R. I mean that particular group where XYZ is belonging to. That group has only the read access to the to that file. And then last three letters are R dash dash. It means if this is, I mean, not for the user, not for the current group, for the others, anybody else has a read access, it that person, I mean, anybody else does not have the write access, they don't have the execution access for that particular program, particular file. So let's do one thing. Let's write, let's open the file. I mean, let's do pico xyz. Let's edit the file. Pico xyz. Pico, Pico, xyz. Enter. So write down ls, and then let's do write out control O, control O, control X. Yeah, enter. Then control X. Okay, we are out of it. Now let's do one thing. Chmod. Let's do 7744 XYZ space XYZ. Enter. Let's do ls minus L XYZ. Enter. So you can see that a new letter has added. Now we have RWX. Before we had RW dash. So now the root user has the execution privilege on that file. What does it mean? Can you do a dot slash XYZ? Dot slash XYZ. Do a dot. No, not comma, the dot slash, no space, dot slash XYZ. No, not dash, slash. I mean the slash. I mean the backslash XYZ, enter. So basically inside XYZ, we put ls command. So we are listing everything there. So that file is executed. So whatever inside the file got executed. That's how we create the executable files. Now you can see that anybody else, I mean like the group, anybody that is in the same group does not have any execution right. Any other user does not have any execution right to that particular file. So the chmod, the privilege system, has some hierarchical process, hierarchical property by which we can assign certain privileges to it. So for further reading, I would like to ask you to go through to do some research on the web, do some research on chmod, and try to see what are the different privilege systems we have. There is a numbering system that just like I added 744. So basically each three block, three character, three letters, it starts with R. The first one is read, second one is for W, last means write, and last one is for execution. So R has 4 bits of information, uh, W has 2 bits of information, and execution X has 1 bit of information. So once we do 744, that particular file acquires the 7 is the user. At the user level you have all information, all privileges. We will revisit this chmod scheme later as well. Let's not overload us with a lot of information. Let's I mean let's do a quick thing. Let's break for until 8 p.m. and then we will come back and we will complete this assignment, and then we will talk about the next topic. Welcome back. Let's complete the remaining part of the exercise. So Shiloh, if you could reshare your screen, we can get back to where we were before the break. Thank you. So we kind of discussed what is chmod. We will discuss it later in a bigger detail, greater detail. But let's do the another command. Since we are in the root folder, let's do chown command. So what happens here? Chown is a command used to change the ownership of a file to a given user or to a group. So you can do chown, and then you can do xyz, xyz, and then you can do tom, enter. So no, sorry, you have to do chown tom xyz. That's the syntax. The first is the username, and that user, uh, no, not xyz. You need to
Oh,
do
Tom.
tom. Yeah, tom xyz. Then yeah, enter. So now if we do ls minus l xyz, enter. Now you can see that tom is, I mean, you can see here root before. If you look at the before ls minus l xyz, it was root, but now it is tom root. So now the file's owner is tom. Root is still the group of the file, but the owner is tom. So basically you are now what happens, root user cannot execute the file. Can you try to execute it ./xyz? Let's see if it still can do that. XYZ, enter. So no, a root user can still execute it, but because it belongs to the group has the privilege to execute it. So, but you know, the Tom cannot, I mean, Tom is the owner of this file. So we have changed the ownership of that file. So that's the chown command. Then there is a chgrp command to change the group ownership of files and directories. So basically what we should do, chgrp, and then we can do, let's say xyz. That's there's a file. Let me see if that is the right command. So you have, let's do chgrp and then do test2, and then xyz. Because yeah, test2, we are giving the group ownership. So xyz. Now XYZ, enter. Let's see what happens. So invalid group test2. Why it is invalid? You have the
Okay, I
valid.
think. Oh, there still is a test too. I think.
Okay, let's do test. I mean, let's see why it is invalid group. Uh, Let me see the ch group command.
Mine
So,
worked for my test ones I created.
oh, okay. So can we do chgrp test xyz as Jennifer is confirming that that worked for her? Test. Yeah, test. T-E-S-T. Test. T-E-S-T, not X. S-T-X-Y-Z. Enter. Yeah, that worked. I don't know why it didn't work for test2, but it worked for test. So now if you do ls minus l xyz, let's see what happens. So you can see here now the group ownership also changed for this particular group, particular user. So that's pretty much it is. I mean,
So
Tom and test. It was
so
Tom and root, right?
so
It
it's
was
not part of the test. The root group is part of the test group.
no. I mean the root is it was by default when the file was created. it was belonging to the user root under the group root, because root user belongs to the root group by default. That's the primary group. But we changed the group ownership of that file. Now it is Tom, and I mean user is Tom and group is test. So that changed. So if you look at your ls-l before, you see Tom root. Before, if you see a few lines ago, it was like Tom and root, and now it becomes Tom and test.
We can
Okay.
look at the lines where the line green is on the end. There's 3 of them. And if you look over to the left, that's what
Right.
he's talking about. Root at the top one, Tom root at the second one, and then Tom test.
Yep.
I'm getting it. Okay. Because it's kind of hard to read through it. So depending what you're doing, you kind of want to look for the colors.
Right.
Okay.
Yep. So is it clear, Shiloh? I mean, do you see that changes?
Oh, yeah.
Yeah.
Can I ask
Okay.
one more question? You probably
Yep.
said it,
Go ahead.
but why after we did like the XYZ thing and the change group thing, why on those 3 did the XYZ turn green?
Oh, the green is for different reason, because we made it executable. I mean, you see the first 3 letters R, W, X. We have a dash, then next 3 letters are R,
Oh,
W, and
okay.
X. So
Yeah.
execution makes it a different color.
Oh, okay.
Okay. So
Cool.
that's pretty much it is. And then we have to, so we are done with the CH group. So that's about it. I think that's the desired things that we wanted to do as a part of this exercise. So as we move forward, I mean, this is pretty much it is. Let's move towards the remaining part of the discussion, the slides. Let's I mean, gather some topics of the theory of the memory management in the operating system now. And anybody has any questions related to whatever we have done this exercise? So, I mean, this is, you can do it yourselves and then take the screenshots. Be sure to paste those screenshots on the Word file, and that's your assignment done. One thing though, some of you are uploading a lot of pictures. So instead of uploading the pictures, what you could do is very simple. Let's say we create a Word document. Let me share my screen and show that real quick before we jump into the discussions. So I noticed it. Some people, I mean, some of you are doing that, but we have a very easy solution. So this is your Word file, and then let us say I'm trying to take a snippet. Let's say let's think I have a screenshot. I mean, I want to take a screenshot of this virtual box. Then typically what I would do is basically I took the snippet. Just a second. Oops, no, not that one. So I have to take the snippet. So here, for example, now I take the snippet, new. So then I will take a snippet of this particular screen area. I don't know whether the snippet is visible to you. So once I take the snippet, what happens here, the snipping tools is like that. This is the snipping tool. Then I have to go there and copy, this one, this particular symbol, copy. Then we do the copy. See, there is a right tick mark. That means the copy is successful. Then you go to your Word screen and then do the Control V. On your keyboard, just do Control V or right click and do the paste. paste options. That's it. So what I am expecting is that you will do all the comments after each comment, or you can if you have uh, enough screen space, then you will take the screenshot of the entire screen after doing all those comments and upload that into the Word file, and upload that Word file as the solution to your assignment. That way it will be very easy for us for me to review. And also, I mean, that's the instruction given how to submit the assignment. So you see, submit a file documenting completion of each task above, including screenshots of the terminal commands and outputs. That's pretty much it is. You can just take a screenshot and paste it there. Just one screenshot should be fine. All the comments, if that includes all the comments. So that's the way we will do the assignments.
Hey, sir, one quick question.
Go ahead.
Yes, that I understand, and I was able to get through all the assignments for the week so far, but in hands-on number 2 and number 3, it asks not only for the screenshots, but also to post your source code, the 3 files from your source code.
Yeah.
I haven't, and it's probably just me, but I haven't figured out how I can save them within the VirtualBox, area, but I can't export them into Windows where I can upload them into your onto the modules, onto the website. Is there a way to export them out of the Linux Mint directory into my normal Windows directory?
Good question. Let me see. I mean, you should not be able to do that because it's a virtual box and they behave as a separate file, but you can always get into this is Mint, right? Get into the operating system. I mean, get into the internet from Linux Mint, and you can up.
I didn't think about that.
Yeah, I mean, that's a possibility. I'm not sure whether this internet is networked with our. I don't know whether our level of installation include that abstraction, but I'm hoping so. So I'm starting up this one. Let's see. I mean, everything is hands-on. So let's see if it is possible. This is a very good point, actually. I mean, we should be able to export the things, but it is sometimes a little bit problematic because the way the files are maintained, they are saved, it may not be that obvious. So let's say now I'm already having some issue with the mouse. Now mouse is back into my control. So let's say I'm there. I'm putting my password and getting into the Mint. And let's see why it is. Oh, that's not. I want the virtual box to be back. Yeah, this is what. So we have it. Let's see if we can get to the Firefox web browser. So is it? Yeah, it is there. So if we can go there. Oh my God. So let's go. A lot of things. Launch. So why application attempted to perform required privilege authentication is required? What is that? So if we do that, I mean, my password I had to do. I don't want to set up things. I mean, if it takes that much of effort, I would do it a different way. I don't think it is a very good option though. So what is this time shift? We don't need time shift. We wanted the Firefox web browser. So let me give another try. Yeah, that's there. So if I go there now, I do learn.ciat.edu. So can I go there? Yeah, it works. So yeah, I mean, we should be able to do that. Sign in, and then we can do, sorry, not that way, Azure ID, and that's my way to get into there. So I have to type my email ID. So there, and then my password. So if I do that, then let me save it. I have to text it. I mean, it is the obvious step, the two-factor authentication stuff. So I have to put the code. Okay, so now if I verify it, it is verified. Yes, now I'm there, hopefully. Yep, I'm there. So if I go to access my class, I can access from my Firefox. Now if I go to the courses, so let's say this one. And then if I go to student view, and then if I go to the modules, let's say I'm doing some hands-on. So install CentOS, start assignment. So upload file, browse. Let me see. So if you save something here, you should be able to see my process is one. Yeah, I mean, that way you can upload those things. But then the problem is I can see that you can upload your code that way, but then what happens to your Word file? You don't have the Word file inside here. So that is a constant source of problem. I think the best way to get it done is basically you have the terminal. So on the terminal, you can have the source code, and you can simply take a snippet of your source code and just submit it. That is
Okay,
the
yeah, I was able to get in through the Firefox also, and I'll see if it'll let me upload files from two different areas. I'm not sure it will, um,
okay.
but yeah, if
That's
not, I've put all the screenshots into the Word document, so I think it's all covered.
okay.
Exactly what I typed and what didn't work and how I fixed it. So, but it just said to upload the three files, and I can see them, but only in the
So
Linux Mint architecture.
so basically, if I have it here, let's say I open the I'm opening the my my own this is my Windows machines file explorer. If I want to get it here, can I do that?
I did it like you said the second time. I just like did a screenshot of the
Oh
code.
yeah, yeah. It is not possible. You cannot drag and drop. Okay, that's fine. You can do the second. I mean, the way I just mentioned. I mean, it's a simple step. We don't have to be. We don't have to stress out for doing that. Just take a screenshot and submit it. I mean, that's
All right, thank you,
easy.
sir. I appreciate that. I
Yes.
appreciate you walking through it.
Yep. That's the easiest way to do that. So let's go to our memory management discussion. So we were talking about the memory management. So basically, what is the memory management? Um, the memory management is a process by which you can organize and coordinate the allocation and deallocation of the memory to meet your program's requirement. So basically, when you run a program, you ran the Python program, the one we were talking about. So what it does, it starts up. So it has to allocate memory um, based on the Python interpreter. Whatever interpreter is doing, it has to allocate the memory. So it first does that, and then once we are done with the program, it exits, right? I mean, once you create the program, the program becomes the process. The Python process is running. Maybe a process has multiple threads. That's what we did. Then the memories are allocated wherever it needs to be, then your program stops execution because it ends. Then your memory needs to be deallocated. So this process to us as user, it's very mechanical to us and it's very obvious to us that there will be something that will allocate the memory, there will be something that will deallocate the memory, but behind the scene the operating system does it. So that's the main feature of the memory management. So the memory management has following four parts: allocate the memory to the processes like the Python process. The Python program, running program is a process, so the Python process. Free up memory when it is no longer required, means the program ends, then you should free up the memory. Prevent the memory fragmentation. Basically, you don't want to basically divide. I mean, you don't want to keep memory occupied by certain things for a long time. So sometimes it happens, especially if you do some connection or some input output stuff going on, then if you don't close the resources properly, even if you close the program, that memory allocated to the file process, they may stay there for some time. There are some programming paradigms like Python, like Java. They have the garbage collector that partially performs that job to reclaim the memory, but that does not do it completely, you know. So in that case, I mean, the system runs into lack of memory situation. For example, if you're running a C++ program, that is the horror story. I mean, you have to do everything by yourself. Now, suppose you are running a database program and you are opening a database connection, you don't close the connection, the database is alive even if your program is not alive. So that connection stays on your memory forever. So what happens then in that case, eventually your database server will be slowing down, and you will have the performance issue. And then what will need to be done, that your system needs to be rebooted, restarted, refreshed, recycled in order to get back to its original situation. So this happens many times. I mean, if you have faulty database connection handling in your process or in your program, then this is common. Now, you need to minimize the memory overhead and computational costs. I mean, so you should not uh, like you should avoid very memory sensitive processes. Like, for example, some of us uses some integrated development environment such as NetBeans, Eclipse, or Visual Studio Code. If our memory configuration is such that we claim very large memory when we start those systems, then that's not a good idea because it will claim lot of memory during its runtime. So other processes will not get any privilege. So in order to do the memory management, these four steps needs to be taken care of by the operating system. Then comes a very important topic called swapping. So it is basically you move the processes between the main memory and the secondary storage. So you have the RAM, right? That's the main memory, and that's not persistable memory. So what happens there? Suppose you write a code. I mean, suppose you are doing something on the word processor. Until you save it, what happens? It stays on the memory. But if you look at the Windows, you will find that those Word documents are temporarily saved into some cache folder, some physical folder. So that means your activities on the memory, what is happening in the RAM, they are copied into a physical space. So that is done by operating system, and that process is called swapping. So you are your word processor using some swapping process to temporarily store your memories, like the draft in the Outlook. Like in the Outlook system, if you start typing some message and then you navigate away from that particular message, it is saved into the draft. There is a process in the Outlook that takes care of that, but at the operating system level, if we have the similar process, then the terminology that we should be using, that is the swapping. So you are swapping the content of a virtual space into the real space. So in the Outlook server, you are typing something, so that is on the fly, but then it is also saved temporarily under the draft folder, which is the physical location. So it is similar to that. So why do you need the swapping? I mean, you need to enable the execution of larger processes by temporarily storing less frequently used processes. Portions of the uh, temporarily storing less frequently used portions of memory on the disk. And also you need to ensure this process, the swapping, makes sure that essential system processes or some essential user processes are not impacted by the memory limitation. So whenever you do some activities, it will constantly, the swapping will not let the memory RAM to be occupied by a single activity. I mean, less priority activity. If you have some root processes running, I mean, the system processes running, that is the highest priority process. It should get enough memory, or some user program is running, that should also get enough memory. So the allocation of the memory among different resources, that's the purpose of the memory management. So when we talk about the operating system, we have, again, we have user space and kernel space. That's what we discussed. Whatever terminology we discussed, uh, many of those things we may not remember, but we should remember that an operating system at its essence, it contains a user space and a kernel space. The kernel space, basically, it has a higher privilege than the user space. So the the activities that takes place in the kernel space specifically, that involves around the functionalities, the controls of the operating system over the hardware resources. So it prevents any overflow of the memory to a particular process. It happens sometimes, but operating system then deprioritize that process, or sometimes even it kills some process. Let's say we are running an IDE. I personally run Eclipse. It's a Java developer tool at my work. I mean, full-time work. I run that excessively. But then if something wrong happens there, something happened, some program gets lost, I mean, out of memory, then what happens, that process becomes unresponsive. That means the operating system invalidates that program or deprioritize that program. Then I had to go there and refresh that process. I mean, restart that system, everything goes back to normal. The user has to take some action. It that becomes inaccessible, a low prioritized, highly deprioritized. So that is the function of the operating system. When you are talking about operating system, it is not a computer program. It is a computer program, but it's not something driven by user. You know, you cannot control the operating system. I mean, how it allocates the memory, how it does several, how it creates the threads, those are controlled by the operating system. And at the kernel's level, the kernel actually makes the, I mean, the user space makes the systems call. The kernel is the one that handles those system call and make all the management possible. So swapping, it is done by the operating system. It's a process within the operating system. It, like you can see here, it does it suspend the process, just like what I was saying, that my process is going out of memory, it suspends that process. So it is not done by me, it is not done by super user, it is done by the kernel, the operating heart of the operating system. So this is the main function of the memory management, specifically the swapping process in the within the memory management scheme that controls those those uh, prioritization, deprioritization, suspension of different processes. So another topic is the memory compaction. It aims to reduce external fragmentation by rearranging memory contents. So basically, you don't want your memory to be fragmented into different processes. So if you do that, then what happens? Part of the memory becomes inaccessible. So basically, it's like that. You have some something, some mouse, some object. You fragment, you break up that object, so it will not be available to many people. So it's something like that. So memory, when we talk about the memory, this is not doable. We should prevent that. The operating system should prevent that. So the benefits of the memory compaction is that it reduces memory fragmentation, of course, maximizes the memory utilization. So the memory becomes available to all the other processes. It helps allocate larger continuous memory blocks to the processes with growing memory requirements. So it basically gives proper attention to the proper processes. Now, there are shortcomings with the memory compaction. Like high computational cost and potential impact on the system responsiveness. So when you have the memory compaction, so then some processes become unresponsive because the processes are deprioritized. Less memories are allocated to that process. Lack of prioritization means memories are not continuously allocated. The RAM is not available to that process continuously. And then, infrequent usage. Second challenge is the infrequent usage in practice due to alternative memory allocation techniques like paging or segmentation. Yeah, if you are dealing with Microsoft Office, the Windows, Microsoft Windows, you will be familiar with the paging. The paging is, each of the it, it behaves like a pages. Each page is a file, and then the memories are kind of snapshotted on the pages. So it can, the paging process or segmentation process, that basically a memory compaction process, and that is a challenge because the memory, the pages in use, that memory is not accessible to the other processes. So sometimes that causes some problem. So allocation of fixed size processes, there can be the fixed size processes that requires a constant amount of energy, memory. That has predetermined memory requirement, and it remains constant throughout its execution. And then you have the allocation for dynamically sized processes. Dynamically sized processes can expand or shrink their memory requirement during the runtime. The dynamically sized processes, good example in the distributed system is the cloud computing, and where you have the load management. You can you can have an option with your cloud computing, whatever you are using. Let's say you are using Amazon Web Service, AWS, or you can be using Google Cloud, GCP, whatever you are using, or Azure. That's what CIAT we use for our canvas management. So whatever system you are using, it has option, it comes with an option with dynamic load management. Those are costly, of course, but it comes with the option. So in that case, you basically tell the operating system, you configure the operating system to allocate and deallocate memory dynamically. And there are challenges of the dynamic process growth. So allocating memory for dynamically growing processes becomes challenging when contiguous memory blocks are not available. I mean, the serialized blocks are not available. And the solutions for processes growth without adjacent memory, that is another problem. I mean that paging or segmentation techniques allow non-contiguous allocation of by dividing memory into smaller units. So basically, that is also, I mean, some feature of I mean, the by which you can grow a process without without allocating lot of contiguous memory there. So you can create the pages and allocate certain memories into the pages. Let's run those processes. Let's deallocate that memory, claim another part of the process, allocate some memory. So basically, you are orchestrating the system to dynamically configure your memory processes. You can I mean you can consider allocating extra amount of memory as well. I mean the recommendation to allocate extra memory, you can do that. I mean you can allocate additional memory beyond a process's current requirement, helps accommodate potential growth. You can do that. I mean that's not a very good recommendation though. So you are basically inflating the memory to different processes. Or you can reduce the overhead. I mean like moving or swapping out the processes that no longer feed their allocated memory. You can just kill the processor. You can just basically invalidate those processes. You can optimize the swapping technique. You can balance the memory allocation. I mean all those things are basically required by the memory management process. And there is I mean you can manage the free memory. Basically you have various algorithms, and there are data structures within your programming that is the backbone to your operating system. They are used to manage the free memory blocks and track their allocation status. Giving you an example, let's say we have we have a system where you can calculate the least frequently used words. I mean, I'm just giving you some example. Let's say we have a keyword management system. Let's say we are on the Amazon web e-commerce center, the Amazon store, and you as a user, for example, someone likes books, someone may like the someone people can have different choices of their products. I'm For example, I may be passionate about the clothings, someone else is passionate about the books, and then within this category of our passion we can have certain things like maybe I like the formal dresses more than the casuals, so things like that. So what are the searching term that I'm frequently using? So basically they can manage their system, their algorithm accordingly. Whenever I go into their system, they will push me towards the most frequently used keywords by me. So those kind of products. So that's an algorithm. So here also in the operating system, um, I mean, you can have different data structures that can have those, I mean, how to manage that can have those indications, those configurations about how to manage the free memory blocks. And then you can have the bitmap based memory management. So bitmaps represent allocation status using the bits. So you have multiple blocks of the memory. You can set certain bits to show the allocation status. So you can have 0, 1, whatever it is. You can show, I mean, if it is 0, let us say there is nothing allocated to that block, things like that. It's not that simple, but it is comparable to that. So so you can have that type of memory management. So you are identifying the blocks and say whether a memory is allocated to that block or not. So it is free. So now it is available for use if it is not allocated. Or and then I mean there are advantages and disadvantages of bitmaps. I mean it is efficient in tracking of free and allocated memory blocks 0 and 1. 0 means free, 1 means occupied. So it's simple to implement, but can be memory intensive for large memory sizes. and they can require additional operations when blocks are even fragmented, or they are merged. So then you can have the linked list, or AVL trees can also be used. I mean, different structures of the collection, like linked list is a list kind of thing. It's like that. I mean, if you already do not know, which is okay. I mean, it is the data structure is the most problematic topic in the computer science. So you can have a collection, let us say. So you can have a list of objects. Oh my God, what is happening? So you can have a list of object. So this one. So you can have a simple collection. You have A, you have B, C, D. There are 4 letters in the collection. So you can access anything randomly. But then when you talk about the linked list, then B is A is pointed to B, B is pointed to C, C is pointed to D. So there is always a pointer from one element to another element. So that makes it easy for basically searching certain things. If you want to do the traversal within the list, it is easy. But if you want to delete, then it's not very simple, because suppose you want to delete C, then you have to take care of this pointer and that pointer and replace it with a single pointer pointing from B to D. So there is some overhead. So those are kind of the data structures. So memory can be managed using those elementary data structures as well. So that was the main goal to mention about the data structure. So here actually it shows the memory allocation. I mean, this memory allocation changes as processes come into memory and leave it. So you can see from A to G, I mean, different processes, different levels of, this is the operating system in the bottom and the processes in the top. So the dashed thing is the free memory. So A comes here, so it occupies that. Then B comes, it occupies that. Then C comes, less memory is available. Then A goes away, so you have this shaded area below B is available. So that way, so this is a fragmented memory. So you have 2 fragmented blocks. You have 2 fragmented blocks in the E as well. So I mean, that's pretty much the way how the processes comes into the memory and goes out of the memory. So the operating system controls these fragmented blocks and tries to recombine those all the times in order that the entirety of the memory is available to the running processes. So, I mean, you can allocate space for a growing data segment. Number A, for example, you can see here, you have the process A. It is allocated more memory than it's needed. So basically, you have this much area, this room for growth. So you are over allocating for B as well that. So you have only this much of dashed structure, this much of free memory here. And you can, I mean, you can also partitionize different, I mean, processes uh, according to its attributes, like the program. Each process has a program text. Then you have the data for the process. Then you have the process itself, the stack, the memory for the process. Now there is a room to grow. I mean, there is a space available, memory dedicated to that process, so that if needed, the process can use it. But this is, I would say, I mean, this is a very dedicated system. For example, if you are using CentOS operating system, hope you remembered how hard it was to install. So basically, it is very memory intensive operating system, because it is used for the servers, where you have everything measured and predictable, most of the things as far as the server programs go. It does not support the users. The users need changes over time. You have 5 users at a time, maybe no user is logged in, and next moment you have 5 users in the system. So that's the Mint Linux. So that needs to be more flexible, dynamical. So that's why it is so simple. I mean, you can customize it easily. But CentOS, for example, it's a server-based system, so it's not that much dynamical. So whenever you run a process, it gets the memory and also maybe the over allocation. So that's why the system is little user friendly. So that's an example. I mean, of between the two systems. So you can there are multiple memory management schemes like the bitmap. I mean all those things. Let's not jump into this. We will discuss the quizzes to address any objectivity questions, or we will discuss the takeout journal to address the theoretical parts mostly. But um, we can just uh, we can see there. I mean basically the processes are these pictures are available in the book, and the processes are pretty much how the memory is allocated. These are the examples of different schemes of memory management. So this one I tend to skip this one as well. So this is important. The virtual memory, there is a need to run programs that are too large to fit in a memory. So solution is basically you need to split programs into little pieces called overlays. You can keep those on the disk and swapped in and out of the memory. But there is another solution is the virtual memory. Each program has its own address space broken up into chunks called pages. You know, I mean, like we see whenever we have the processes, list of the processes, the memories are as if, I mean, the abstraction of the operating system looks like as if all the processes are running concurrently and each has having its own memory space. That is the virtual memory. I mean, in practice, that is not like that. It is the constant swapping takes place to allocate and deallocate memory from a process to another process. So there can be many memory management algorithms, first fit, next fit, best fit, worst fit, quick fit. I mean, these are the examples which we will be discussing. But let's take a quick break and let's come back and let's complete another assignment, and then after that we will get back to the discussion again. For the slides, actually we will be skipping most of the terminology centric stuff. We will be focusing on the basic stuff. I mean what we can understand by common knowledge. We don't want to jump into a lot of terminology, a lot of picture intensive things, because we are trying to make it very simple for us to know the basics. It's not something advanced level knowledge that we want to gather. We want to gather the basics here. So let's give a break and let's come back around 9 p.m. and we will continue with the next assignment. So what is the next assignment? Let's take a quick look at it so that we get prepared about how we are going to manage that. So let's see, hands-on. If I come here, so memory modules, and then we can do the bash, or what is it? Let's see, introduction to the bash script. Yeah, that is a very good topic to discuss. Yeah, so next hour we'll be focusing on that. Let's give a quick break, and let's come back around let's say 9:05. I mean, let's give a 15 minutes break and come back for the next assignment.
I'll do it.
Sure, go ahead.
Let's see.
So let's do the which one? The bash introduction to bash script.
Here's my, all right. Very simple. Where's my share? It's right there.
Yeah. Yep. Here,
Okay, hopefully you can see it.
I can see it. This is your Mint Linux. So we can do this one. Like let's do. Um, you have opened the terminal, so we can skip step number 1 that is done already. So let's create a new directory. Let's write the command mkdir. That is the command to make a directory. Mkdir and then space and give lab assignment, lab underscore assignment. So that's yeah, enter. So we have created that, and then we have to change to that directory. So let's do cd and then space, write lab and put the tab. It will be there. Just
The whole part lab.
press tab. You will see
Oh,
that.
okay.
No, cd space
Yep.
lab, and then if you press your tab button, you will get all the remaining. Yeah, that's what.
Oh.
It's a shortcut. So enter. So you are in the lab assignment, that folder. Now, what you need to do is you need to create a script basically. So this class is about the shell scripting. So just giving you a little bit introduction. I mean, Bash is a shell, and we are focusing today, I mean, here in this assignment about write the scripts in Bash. What is the purpose of the script? It is to manage different tasks within your system. It's like an inline program that will use a lot of systems utilities to manage a lot of programs on your system. We are going to see that. So
Is
let's
that kind of
do
like a .bat file?
kind
in
of,
Windows?
yes, the batch
Okay.
file. Exactly. You
Yep.
are exactly the right point. So let's do touch, touch, touch. It is the
Oops, I
command.
lost my mouse. Let me get my mouse.
Oh, okay.
There we
Yeah.
go. Okay.
Touch and then hello underscore world.sh. World.sh. So you are creating a shell script named hello world. Enter. So a new file. If you do ls, you will be able to see this hello world. Yeah, so you see that, but it is 0 byte. It's an empty file right now. So in order to, so we have created a bash script basically. So now we can use the command nano and or pico, whatever you want. Nano hello world, that's fine too.
They both do the same thing.
Yes, they are the editors. They are not the exactly same program, but they both are editors. You can always do tab to shortcut the things. Okay.
Oh yeah. Okay. Yeah.
Enter. Yeah. So yeah, Nano and Pico, they look similar. So let's write the content of the script right now. Let's do echo, 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 and then space. Then let's put a double quote, hello world. Hello world. Yep, that's good. And yep, and then do control O, enter, and
Yep.
control X. So you are out of this program. Okay, that's good. So once you do that, I mean, now what you have to do chmod. We have already learned about chmod. Then we want to execute this program. So let's add space and then plus X. That means you are adding executability to that program. So plus
The actual plus sign. Okay.
yes,
Yeah.
yes, X. No, do no space in between plus and X. And
Okay.
lowercase x,
Yep.
and then space hello, and then put a tab. You will just write H and put a tab. You will get everything. Yep.
Okay.
Enter.
I gotta
Enter.
I gotta play with that tab. Okay.
Yeah. Yeah. So now it is executable. So now what you should do is dot slash H tab. Yep. Enter. So you create your first bash script, shell script in Linux. So basically what it does the echo command. This command you can do it command line as well. If you write echo and then you write something, just type echo and then space and then double quote, do something, write something, double
In the
quote
double
and
quotes now.
yeah, double quote. Yes, put a double
Okay. Oh, you
quote
cut out a little. Okay.
and then,
I like ice cream.
okay, enter. So yeah, so echo is a command. I mean, it's a command line thing for the um, for the Linux, and basically when you write a bash, I mean shell script, you are putting all the stuff that you would use in the command line. So basically you are automating, like the Windows batch file, you are automating the execution of those files. So that's the first thing we have done. Now what we need to do, number two, let's go to number two assignment. In this particular assignment, now we have to write a bash script that takes a user input. So here we didn't provide any user input. So let's do nano. um, let's write nano and then user underscore input dot sh. User underscore input dot sh. So you are creating a file without using touch command. Enter.
Okay.
So your file is created. Now you will do little bit of things. So so what you can do here, you can do just like the exercise says. I mean, uh, what happened to that?
The pound
Oh, okay,
exclamation.
yep. So do the pound, yes, not slash bin slash bash slash bash. So it means that this command means that if your shell is not specified when you enter the system, not in the nano, but when you log into the system, then by default it will adopt the bash shell to execute the program. So this is the implication of this line. So you do pound. I mean, it is generally a comment, but basically it says that if your system, if your shell is not a bash shell, then your then you should be using the bash shell for executing this shell script. So let's go to the next line and do echo and then space, you know about it, space and then yes, enter your name. So you are instructing to the system, okay, enter. Then you can do read name. So you're reading something, and then you can do echo, next line, echo, and then space, double quote, hello, and then dollar name. Yeah, I mean, that's fine. And then space, dollar name. So dollar name, and basically name is a variable. In bash, every variable is in the shell script, variables are designated by the dollar symbol. If you are familiar with PHP language, then it will be like that. I mean, variables are like the dollar symbol. So let's do control O and then control X. No, control O. Yes, and enter
Yep.
and then control X.
X. I always want to do Q for some reason. X.
Oh, no.
Oh,
Control
right.
enter, just enter. And then control X.
Okay.
Yeah. Now do chmod plus X and then user input dot sh.
Underscore.
Okay. User underscore input.
Underscore. Okay. I'm like,
Yep.
is there one there? And then nothing.
Yes, and then dot slash user input. So you should be prompted. No, not that. I mean, that is
Oh,
fine,
okay.
but then you have to do dot slash. I mean, no more chmod plus x. Just remove these texts from this line.
Okay.
Yeah, dot slash
Aha.
user input. So you and then just put tab.
Oh,
Yeah,
yeah, I keep forgetting I
yeah,
can do
yeah,
that.
yeah. Enter. So write whatever you want to put, yes, and then enter. So here you go. So now you have the capability to read something from the command line. So many times actually when we work in for a in an enterprise, we do, I mean, a lot of programs where you are prompted to do some some information, and then this is the way you read it from the bash, I mean the shell script. So number 3, let's go to the program number 3. It's very simple. It's let's open let's do nano and then numbers.sh, the next program's name, numbers.sh. So in this exercise we will be focusing on looping the for loop. So let's do the usual, that is hash uh, and then exclamatory slash bin bash. Yes, that's good. And the next line, it should be, now we are trying to do some for looping. So for I, yes, in space in, and then within a within the brace, curly brace, 1 to 10. One,
Is
yeah,
it one
yeah.
dot dot? Okay.
So what does it mean? We are basically looping. I is a variable which is looped between 1 to 10. Do, yes, you are now asking the compiler to do this looping. So in the second line, you basically say a structure. You create a kind of cursor. It is called a cursor, but basically you are creating a structure. Define that you declare that I is a sample variable which can be looped for a value of 1 to 10. Now, third line, you are instructing the uh, basically compiler for the bash. Compiler is the bash shell. You are instructing that shell do this looping. So now do, and the next line you can go and then press a tab so that it looks good. Yeah, echo, and then you do $I. So because dollar is the symbol of any variable in the shell script, then go to the next line and do done. So do is ended by done. So that
Okay.
is the terminology. So you have the for loop. This is a single block of code. You define the for loop. You are saying what you want to do there. Proposition. Then you ask the compiler to do that for loop. So you start with do, whatever statement you do there, you can do echo, you can do any calculation, whatever you want, followed by done. So you have completed that job. So if you now do control O, enter, and then control X, you will come out of it. Yes. Now you do chmod plus X, then n tab. You can do the tab. Yeah. Enter, and then dot slash numbers. Yeah. Enter. So you see that these are sequentially showing up those numbers. So we got this, I mean, this for loop as well. So basically, this is the subject matter of this assignment. So basically, what I expect is there you do each assignment, take a screenshot for each one of them, take a screenshot of your script, take a screenshot of the outcome of the script. Like here, you do nano and take a screenshot, and then you execute this script, take the screenshot and paste it into the Microsoft Word document, and that's it. I mean, that's all we need here. Upload that to your assignments. So this is super easy. Any question, anyone? Okay, so then we can move towards our remaining discussion. So this is really quick. Thanks, Jennifer, for sharing your screen.
Yeah, no
This
problem.
is, yeah, this is helpful for all of us actually. So it's a very nice collaborative way we are learning the things. So let me share my screen and let me go to the remaining part of our topic today. Um, okay, so this is that one, and then I have to open this one. So we were studying about the virtual memory. So there are different memory management algorithms. So you can manage the increasing software sizes. I mean, software sizes have been um, growing faster than memory sizes, leading to need to run programs that exceeds the available memory. Like, I mean, the bash script that we were talking about, that's a very simple script. It doesn't require a lot of memory. But imagine that you are uploading a picture, you are reading a picture pixel by pixel inside your bash script, then you will definitely need a lot memory than what we are using here. So that's a typical usage of a memory intensive program. Or suppose you are running some artificial intelligence program, some AI tool. Let's say we want to do some natural language processing, meaning you are training a set of words uh, with the known samples, and then you follow that training sample to predict on some words that's given. So I mean, those tasks are very memory intensive. Just giving you an example, like there are tools in the AI. For example, if you want to write some topic, let's say you want to write about yourself, but you want to adapt like Arthur Conan Doyle, I mean, famous novelist, his style, versus you can do, let's say, any famous writer, whoever that is, their style. So what it does basically, it stores different authors' writing style in their database, and then it trains the system accordingly. And then in the third step, you write that something about yourself on the screen, and then uh, it basically projects your writing as per their style. I mean, this is the example where you will need a lot of memories. So those processes, I mean, uh, require I mean, it requires more memory than your system has. So in that case, you need some virtualization of the memory so that you can segment your processes into steps. Each step is given a smaller block of memory, and then it is done. You go to the move over to the next process. The beauty of this thing is that you don't need to like manage this swapping process. The operating system is responsible for that. Then you can have I mean, using the virtual system, you are supporting multiple programs at the same time. So just as you open your taskbar on the Windows and you see that 100 processes are running, so that is all the virtual memory. uh, so then there are challenges with the swapping. I mean, you can swapping the programs in and out of the memory. It can be time consuming for the operating system. So that's why um, so if that requires a lot of access to the hard disk, so that's Conan Doyle word processing process, AI tool. So it requires a lot of access to the database, to the file. So that is expensive. So it may it may result in a significant overhead in the swapping process itself. Then in the past, programs were split into small pieces. These are called overlays. And then with an overlay manager, loading and running the required overlays in the memory. So I mean, basically, you can split the program into small pieces. So that's the same thing we are talking about again and again. In different slides, we are talking about basically the same thing, but we are giving different perspectives. That's all about the operating system. It's like you are defining some process, defining some scheme, and then you use it, you extend it to for some different purposes as well. So that's why it is called extended machine, the operating system. So then you can split the programs into overlays. I mean, that was a manual process, and error prone tracks performed by the programmers. You can split it, split each program into different process, but that's a I mean, that's basically, if you do it, if the programmers do it, that may create some errors. So virtual memory is there to rescue from those manual processes. So basically, these are the main benefits of using the virtual memories. I mean, the last one, you get rid of manual process initiated by the programmer. You get the operating system in charge of it, and then yeah, go ahead, Shiloh.
I was just wondering, I know you probably might have answered this. So all of these things that we're talking about, like when we do word processing, calculator, wanting to print something all at one time,
Mhm.
how does the operating system or the kernel know, probably through algorithms, probably, how does it know which one of these like to use? Like, how does it know when to use the virtual memory or
Mhm.
swapping or paging?
Yeah, that's a very good question. So uh, what happens in the operating system, in the kernel? So they have algorithms, they have the programs basically that calculates the memory of the process. I mean, when you compile a program, when you run a Python program, when your interpreter, that time your interpreter makes an assessment of how much memory it will take, then behind the scene the interpreter transfers that information back to the kernel, and then your kernel gets that information, and then it says, well, it requires more memory than my system has available for
Oh,
each of the processes. Then it does some mapping, and then it splits the execution into multiple virtual spaces, or the pages, multiple pages. Once the first page is done, let us say you run a for loop, then it does its magic. The operating system, it reads through the for loop, and let's say you are running a loop from 1 to 10. Let's say it splits the process for each of the loop. It does the calculation. So page number 1, it does the calculation for I equals 1. Page number 2, it does the calculation for I equals 2. I mean, it is not the exact way it is doing, but I'm just trying to give a portrait of what is going on behind the scene, what can be going on. So then at the end of that, end of every calculation, from the instructions from the Python interpreter, it consolidates the results, and then it initiates another process. It creates another page where it throws the result, transmits that result to the terminal window. So basically, operating system gets the estimate from the program, the process. In our case, the process is running on the top of Python interpreter. So it gets some interpreter, some information from the interpreter, and it processes that. I mean, it processes that execution of the process by segmenting the memories. So it is the interaction between interpreter and the operating system.
oh,
Yeah. So this that's why you will see when you download Python, you will see it offers you distribution for Windows versus distribution for Linux versus distribution for whatever operating system it is. Because in each of the distribution, the Windows distribution, it knows how to deal with Windows kernel, how to deal with Windows, whatever the heart of the operating system. When you are downloading Linux on a Linux system, that particular distribution, the Python interpreter, which is also a program, it knows how to deal with the Linux operating system. To us as programmer, they are all same. They are Python interpreter. We don't go inside those, but that is happening behind the scene inside the interpreter and its interaction with the operating system.
Oh,
So that's how it knows. Okay. Thank you. So that's a good question actually, because I mean this is a relevant point in respect of the memory management. So here actually you can see the position and function of basically what is that? I mean you are doing memory management unit. I mean it's a virtual unit. I mean there is nothing you can see in your device that this is my memory management unit. You can see that it is all virtual within the programs that drives the operating system. You define some section called memory management unit. It's a virtual section, and then they are actually the, this memory management unit is connected with the physical addresses of the memory, and this information from one part to another part, this information is carried by the bus. Bus is some kind of hardware system which actually carries the signal. It's the bus. I mean, right, public transportation, the bus we have that carries us from one point to another point. Similarly, the system bus, the operating system bus, carries the memory or information from one segment to another segment. So it carries the memory. It carries the program basically. Whatever happens in the program, it has a mapping of the program has a logical distribution of memories, the chunks that you were talking about. So the pages, these pages are having specific information. This information goes to the memory, the CPU, sorry, the RAM of the system, and that is carried by the bus. And then from memory, it goes to the disk, basically hard disk. You are saving some information. The pages are saved one by one, and then it is swapped. So that's why, it takes little time by the bus. I mean, it's a signal processing system to go from one place to another place. So, I mean, the bus is, I mean, these things, I mean, memory here, whatever we are saying, it is all virtual. But there are some registers, some signal processing units, which is a subject matter, which is a topic of interest by the advanced electronic systems. So if you learn electronics, you are not required to do that here, but if you learn electronics, you will see how the buses work. I mean, people who learn, let's say, the physics, they learn a lot about it. So basically, you have a electronic circuit design, and you can see. I mean, you can design by yourself, uh, like a prototype of a signal processing unit. So it's like a wire, like we switch on the light and the electricity goes to the light bulb from the distribution center. So this is also modeled after that. I mean, that is the most elementary process. But basically, what operating system does is it orchestrates the information processing between the software process, the virtual process to the hardware process, because ultimately hardware process is the one that processes all the signals. So operating system establishes a connection between software and hardware, and the memory management unit is the central to all these management by the operating system. So I mean, each program has its own address space. I mean, we already went through that. So basically, uh, we know that whenever we initiate the task bar, I mean the task management system, you have the I mean different tasks are assigned to different memories. It looks like each of them has some virtual memory, but the memory works in its entirety. But this virtualization, it is done at the operating system level, so that so that they can support multiple process, the multi-programming model. Then it is able to map the pages on the fly. I mean, basically, you don't have to write everything in black and white. You can simply it has the ability to do the calculations on the fly, and so it basically makes use of the registers to carry the signals from one point to another point. And then there are information regarding paging versus segmentation. Most systems nowadays use paging, where fixed size units are mapped. So paging typically is a Windows feature, but right now all systems use the paging. But the segmentation is basically segmenting the memory into different sections. So, I mean, segmentation is associated with variable size, whereas paging is associated with fixed amount of partitions. That is the difference between paging and segmentation. Now, in the multi-programming system, the main benefit is that you have the virtual memory. The virtualization of memory allows supporting of multiple programs to run at the same time. So each of them can get fair share of the CPU. So it is controlled by a program. It does all the memory allocations, and these memory allocation process creates something called virtual memory, and that supports the multi-programming model in the operating system. So I mean, virtual memory system utilizes paging. This is an important concept. It's a common technique of memory management. Paging is a technique to manage the memory. As I said before, when you do the paging, you are relying on dividing the memory needed for the program in equally uh, segmented sizes, equal sizes. You are basically creating chunks of different I mean segments from the main memory, so that you can uh, you use the bare minimum whatever is needed, and then you keep the rest of the memory available for other programs. So that's a model for the multi-programming model. Now the programs generate virtual addresses that form the virtual address space. In systems without virtual memory, the virtual addresses directly access the physical memory, which is very inefficient process. In the virtual memory system, virtual addresses are mapped onto physical memory address through memory management unit. So whenever you need the virtual memory, whenever the advanced operating systems support virtual memory, like the devices that we are working, they have the virtual memory, and this virtual memory is connected to the main memory using a system called memory management unit. As I said, there is no hardware component. There is no box called memory management unit, but it's a software process. It's a process within the operating system that orchestrates that memory management, like the paging or segmentation, whatever you want to do. The pages and page frames are typically of the same size, equal size, such as 4 kilobyte. The mapping virtual pages to page frames allows dynamic loading of the program segment from disk or hard disk or solid state device as needed. The MMU, Memory Management Unit, handles the translation of virtual addresses to physical addresses based on the mapping. So there is a lot of things going on behind the scene. So you define a virtual memory. I mean, basically you virtualize the memory. The virtualization is accomplished by a set of programs or the set of processes. Inside the program, all the mapping between your software space to hardware space is performed. your software program creates certain signals that interrupt the registers, and that initiates some buses, so that the information is carried from your memory management unit to the actual memory, and then subsequently to the disk itself. So it's all, operating system, as we see here, the virtualization, whatever we are doing, the virtual machines, they are orchestrating all the memory management process that happens behind the scene. As a programmer, as a end user of the system, we don't have a feeling about those. We use those as a black box. We are all confined to the user space of the operating system. And all these things are taking place in the kernel space, so that, operating system can do all those memory managements. So here, typical examples, the virtual address and physical memory. So you can see the virtual address spaces in the gray color, and blue color is the physical memory. So you can have mapping, correspondence and mapping. So basically you can have some unclaimed spaces in the virtual page, and you can have some dedicated, when you get your programs, you see your virtual memory is always more than the physical memory, because you create a lot of virtual spaces, and then you create you carry that information to the real memory, and you have an algorithm in the operating system, has an algorithm to make the correspondence between the virtual address to the physical address. And that's why whenever you run a program, it takes little time to be executed. It's not, it varies from one program to another program as far as the memory consumption is concerned. So if you have a very memory intensive program, then you have more time for it to be executed. Um, so a simple example illustrates the mapping of process. Like 60, the one we just discussed. Here the 16-bit virtual addresses and 34 kilobyte of physical memory. So virtual address space is divided into 16 virtual pages. Each has 1 bit of size, while physical memory has 8 page frames. The memory, that's what I was saying, that MMU, it does the mapping of the virtual addresses to the physical addresses. It allows the access to the corresponding data, and pages not mapped to physical memory are indicated as crossed. Here, this one. Basically, you are mapping the virtual space pages to the real memory. So you got to get a program like Shiloh's question. How does it know? So Python interpreter gives you the estimate that your program requires 64 kilobyte of memory. Then it creates these virtual pages, it segments, and then it does not have 64 kilo memory. It has 32 kilobyte memory accessible for this program. So one by one, it takes care of the pages, and then at the end of the day, once it is done, then it accumulates all the information back to back. It has the pointers to keep track of the progress of the program. Then it sums back everything that is done in the program and delivers to the user. So that's what is happening behind the scene. So the page tables, they serve an important purpose in that. They serve the purpose of mapping the virtual pages to the page frames. The page table acts as a function with the virtual page number as the input and the physical frame number as the output. It's a mapping. So like a database table, lookup table, it's like given a physical, virtual address, it gives you the physical address. So it creates that correspondence. And the page table entry structure may vary across different operating systems, but it includes information such as the page frame number and the bitwise operators. So that's another thing. The accessing a page table entry with the absent bit sets causes a page fault. You know, if you want to access a page table entry, but your bit set on your actual memory is absent, then it's an error. It creates an error. So I mean, all those things. I mean, basically what you need to remember is that you have virtual space, you have the real memory space. These correspondence is done by a mapping, and the mapping information is contained in a table called page table. Table is a file, basically a system file that contains all those information. Those files are not in general accessible to the users. They may not be in the ASCII format at all. They may be in the binary format, whatever format, I don't know what format it is, but they are not accessible to common user. They are the systems, I mean, the kernels, they live in the kernel space. So there are fields in the page entry. So you have the present absent bit indicates the validity. 0 means not in the memory. You have the protection bits to determine access permissions. That's what we were talking about. Like you set a resource on a particular group, and a user ABC is not within that group. So that's the protection bits. I mean, that's the reflection of the protection bits. It happens behind the scene. And then you have the supervisor bit determines the accessibility, privileged code or user programs. I mean, the root user, they can basically assign that accessibility. They can set the supervisor bit, the status of the supervisor bit. The modified and referenced bits track page usage. I mean, basically, you have multiple fields in the table entry, and they have certain purposes. So the most important is the present absent and the protection bit. Those are the important. I mean, there are other fields as well in this context. So you have the disk address. I mean, that's not part of the page table. The page table holds the necessary hardware information because page table is a mapping. The operating system manages the page fault handling. I mean, operating system is a software program. It's not hardware. So it handles the error handling for the pages. The virtual memory creates an address space abstraction. That's what we were talking about here. This one, this is the address space abstraction. And all memory accesses, including the operating system, they use the virtual addresses. So basically, we did, I mean, we explained the basic concept of the virtual memory and how the virtual memories are mapped to the physical memory. So you can do the paging process is slow because it requires the actual access to the actual memory space, right? So there are two challenges. I mean, fast virtual to physical address mapping, efficient management of large page tables. So basically mapped speed. So mapping speed is crucial, and page table should not be excessively large. I mean, all these things as a user, we cannot control. This is control at the operating system level. So the computers, they have usually huge virtual address spaces. Large page table size becomes impractical. I mean, those are the things that are included in your operating system program. And so basically all the operating systems, they are built to speed up the paging, but you can have different clock speed. I mean, different system speed. There's come the processors. I mean, more speedy your processor, more speed. I mean, your paging process is much faster. So that's why you pay money to buy an advanced processor, or maybe you can have the multi-core system so to speed up the paging process. Now, in some CPUs, such as different things, I mean, the CPU vendors, the software manages the um, TLB entries. I mean, what is TLB entries? We need to know. I don't know what is TLB entries. There must be something going on there. TLB entries. So basically, translation look aside buffer. I mean, it's a terminology. So basically, it's something something happens in between the correspondence between the virtual memory and the physical memory. So I mean, the TLB is an interface in between, and it is managed by MMU. That's all we need to know here. I mean, memory management unit that that manages the translation look aside buffer, or TLB. So there can be missing. I mean, the translation can be faulty. So you can have the soft misses and hard misses. The soft misses occur when the page is not in the TLB but in the memory. I mean, there can be inconsistent. That can be in the inconsistent state. So the software, the memory management unit handles all those things. Um, there can be page tables. I mean, with the large memories, I mean, different page tables. I mean, we have to basically we have to tune the page table in a way that the correspondence is faster. So I mean, you can have a lot of large memory in the you can have lot of processes with considerably large memory. So you have to tune your page tables to handle those. I mean, you means the operating system. That's the challenges in the operating system. So these are some empirical diagram. Let's keep this. So page table entries, you can see the page frame number. I mean, these are um, the entries for the page table. As I say, the present absent, and also I mean, the protection. These are the essential things, but there are other fields as well. So that's what we already discussed, how to speed up the paging. There are two challenges from mapping issue from virtual to physical address. And if the virtual address space is large, the page table will be large. So that's pretty much it is. And it is so TLB, the interface translation look aside buffer, they create the buffers to hold some information on the fly. So they are used to speed up the paging. So there are examples of different levels of paging, but I think we can get a decent stop here, because there are multiple things. I mean, the page replacement algorithms. I mean, these are the multiple complex discussions we are running into. So we can set a stopping point here. And I think, I mean, what we should do, we should basically think about the basics, like whatever we learn in the memory management process. So what we have learned here is that operating system, one of the functions of the operating system is to perform the memory management for us, for the whole system, for the whole device. Now, in order to do that memory management, there is a way. I mean, previously we did not have any um, virtual memory. So everything was tied to a hardware memory, which is inefficient because you have to use a disk input output. Nowadays, modern computers have virtual memories, means you have basically you can accommodate more memory than your system has. You can run a program with huge memory that requires huge memory, but your system may have less memory. So your operating system basically generates a virtual memory space, and it establishes the correspondence between virtual to real memory space. So for that purpose, you need to generate the pages. Pages are the softwareization of your hardware. So basically it creates the segments, and it dynamically stores and removes that information. Now the page, the communication between the memories and pages are done by certain buses, and whole process of memory management is done by the memory management units. And you can basically you can speed up the pages by accommodating the buffers called TLB, or translation look aside buffer.